Hello everyone. Welcome to the class of Highway Survey and Design. I'm Wen Jiaqiang, the main lecturer. The design of vertical curves primarily encompasses the definition, elements, and calculation formulas of vertical curves, determination of the minimum radius and lengths of vertical curves, key points in vertical curve design, and calculations of vertical curves. 5 aspects in total. Last time, we covered the first 4 aspects, and today we will focus on vertical curve calculations. Vertical curve calculation refers to determine the design elevation as specified stake numbers on the longitudinal profile design line. Let's consider an engineering case provided by a company. In line with the strategic requirements of rural revitalization, a county plans to upgrade a forest-class highway leading to a mountainous area to a secondary highway, so as to better serve local economic development. The road includes a vertical curve with a stake number of a grade change point, K3 plus 030.00, an elevation of 427.68 meters, a front slope I1 of positive 5%, a back slope I2 of minus negative 4%, and a radius r of 2,000 meters. Please do the following. 1. Calculate the elements of this vertical curve. The slope rotation angle, omega, curve length, L, tangent length, T, external distance, E, and determine the convexity or concavity of the vertical curve. 2. Calculate the starting and ending stake numbers for this vertical curve. 3. Calculate the design elevations at stake number K3 plus 000.00 and K3 plus 100.00 on this vertical curve. Let's calculate them one by one. 1. Calculating the elements of the vertical curve. Using the previously learned formulas, the calculations are as follows. The slope rotation angle omega, the difference between I1 and I2, is equal to 5% minus negative 4%, resulting in 0.09. The curve length L equals the product of the radius r and the absolute value of angular velocity, where r is 2,000 and multiplied by 0.09, resulting in L being equal to 180 meters. The tangent length T equals L divided by 2, which is 180 divided by 2, resulting in 90 meters. The external distance E equals T squared divided by 2r, where T is 90 and r is 2,000, resulting in a value of 2.025 meters. Since the slope rotation, omega, equals 0.09 greater than 0, the vertical curve is convex. 2. Calculating the starting and ending stake numbers for the vertical curve. Using the vertical curve calculation formula, the process is as follows. The starting stake number, KQD, equals K3 plus 030.00 minus 90.00, which is equal to K2 plus 940.00. The ending stake number, KZD, equals K3 plus 030.00 plus 90.00, which is equal to K3 plus 120.00. 3. Calculating the design elevation as specified stake numbers on the vertical curve. First, identify the position of the specified stake number and calculate the vertical distance h. There are 3 possible positions for a specified stake number on the vertical curve. 1. On the straight section. 2. On the first half of the curve. 3. On the second half of the curve. Since the calculation of the vertical distance h varies with each position, it's necessary to determine the position of the specified stake number before calculating. For K3 plus 000.00, as it is greater than the starting stake number K2 plus 940.00, and less than the grade change point K3 plus 030 33.00. It is determined to be on the first half of the curve, which is situation 2, where the horizontal distance L is the difference between K3 plus 000.00 and the starting stake. Thus, at the point K3 plus 000.00, the vertical distance h is determined by taking the square of the difference between K3 plus 000.00 and K2 plus 940.00, then dividing the result by twice the radius 2r, resulting in a value of 0.90 meters. For K3 plus 100.00, since its stake number is greater than the great change point K3 plus 030.00, but less than the ending stake K3 plus 120.00, it can be judged that K3 plus 100.00 is on the second half of the curve, which belongs to case 3. At this time, the horizontal distance L is the stake number difference from K3 plus 100.00 to the ending stake. Thus, the vertical distance h equals L squared divided by 2r, where r is calculated as the square of the quantity K3 plus 120.00 minus K3 plus 100.00, divided by 2 times 2000, resulting in 0.1 meters. If a specified stake is on the straight section, the vertical distance h is equal to 0. Then, calculate the tangent elevation HQ at the specified point. The formula of a tangent elevation HQ equals the great change point elevation plus the product of K required minus K BPD and the slope I. Pay attention. In the formula, if the specified stake number is less than the great change point number, then I equals I1. If greater, then I equals I2. For K3 plus 000.00, since its stake number is less than the great change point K3 plus 030.00, then I is I1, which is 5%. Therefore, the tangent elevation HQ at K3 plus 000.00 is 427.68 plus K3 plus 000.00 minus great change point stake number K3 plus 030.00 times 5% equals 426.18 meters. For K3 plus 100.00, since its station number is greater than the great change point station number K3 plus 030.00, the slope I equals I2, which is negative 4%. Therefore, the tangent elevation HQ at K3 plus 100.00 is 427.68 plus K3 plus 100.00 minus great change point stake number K3 plus 030.00 multiplied by negative 4%, which is 424.88 meters. Finally, calculate the design elevation HS at a specified point on the vertical curve. Instructed point's design elevation HS equals the tangent elevation HQ of that point minus the quotient of h divided by the absolute value of omega, where h is the height and omega is the angular velocity. The design elevation HS at stake K3 plus 000.00 is 426.18 minus 0.9, which is 425.28 meters. The design elevation HS at stake K3 plus 100.00 is 424.88 minus 0.10, which is 424.78 meters. With that, our calculations are complete. Lastly, it must be emphasized that vertical curve design is not only related to driving comfort, but also to safety. Therefore, the design elevation of a vertical curve must be carefully designed and accurately calculated to avoid potential risks to public safety and property. In this lesson, we learned about the calculation of vertical curve. Have you mastered it?